Nylon 6, also known as polyamide 6, stands out as a crucial engineering polymer in FDM 3D printing. Its toughness, flexibility, wear resistance, and thermal stability make it ideal for manufacturing gears, automotive brackets, fixtures, and prototypes. However, despite these advantages, Nylon 6 presents unique challenges during the printing process. Its hygroscopic nature and tendency to shrink thermally can lead to several defects. This advanced visual guide will explore the major difficulties encountered when printing with Nylon 6, their underlying causes, and the engineering solutions that help overcome them. Let's begin by understanding why Nylon 6 is so widely used and what makes its properties both a blessing and a challenge. One of the most significant challenges with Nylon 6 is its rapid moisture absorption from the air. This hygroscopic behavior means that the filament can become wet very quickly, even before printing begins. When wet filament is extruded, it produces popping sounds, bubbles, rough surfaces, poor layer bonding, and severe print defects. These issues not only affect the appearance of the printed part, but also its mechanical strength and durability. Moisture absorption is a critical factor to monitor, especially in environments with high humidity. Understanding how moisture impacts the extrusion process is essential for achieving high-quality prints with Nylon 6. Thermal contraction during cooling is another major issue when printing with Nylon 6. As the material cools, it shrinks, which can cause dimensional inaccuracies in corner lifting, especially in large parts. This phenomenon, known as warping, leads to parts that don't fit their intended purpose or fail to meet design specifications. Edge lifting is a common symptom, where the corners of the print detach from the build plate. Managing thermal shrinkage is crucial for maintaining the structural integrity and accuracy of Nylon 6 prints. Proper thermal management and enclosure design can help minimize these effects. Nylon 6 often struggles with bed adhesion during the printing process. Due to its low surface bonding properties, the material can detach from common build plates, leading to first-layer peeling and incomplete prints. This issue is particularly problematic for prints that require a strong foundation or precise dimensions. Ensuring proper bed adhesion is essential for successful 3D printing with Nylon 6. Solutions such as using specialized build surfaces, adhesives, or adjusting bed temperatures can significantly improve adhesion and reduce print failures. Stringing and oozing are common defects when printing with Nylon 6. The molten polymer remains fluid for longer durations, which leads to the formation of unwanted thin strands between printed parts. These polymer strings can affect the surface finish and overall quality of the print. Stringing is often caused by high melt flow and improper retraction settings. Addressing this issue requires optimizing printer parameters such as retraction speed and distance to minimize the formation of strings and ensure cleaner prints. Layer delamination is a serious defect that occurs when interlayer bonding is weakened due to improper thermal management. This results in cracks forming between layers, compromising the mechanical strength and reliability of the printed part. Uneven cooling and unstable chamber temperatures are primary causes of delamination. Maintaining a stable printing environment and optimizing cooling rates are essential to prevent this issue. Delamination not only affects the appearance but also the functional performance of Nylon 6 components. To address the challenges of printing with Nylon 6, specific printing parameters are recommended. The nozzle temperature should be set between 240 and 280 degrees Celsius, while the bed temperature should range from 70 to 100 degrees Celsius. Drying the filament at 70 to 90 degrees Celsius before printing is crucial to prevent moisture-related defects. Using an enclosed chamber is highly recommended to maintain stable thermal conditions and reduce warping and delamination. These parameters help optimize print quality and minimize common defects associated with Nylon 6. Summary table of engineering solutions provides a clear overview of how to tackle each major challenge in Nylon 6 printing. Moisture absorption is managed by filament drying and using a dry box. Warping is reduced with a heated enclosure. Poor adhesion is solved by using gurulate surfaces and glue sticks. Stringing is minimized through retraction optimization, while delamination is prevented by maintaining stable chamber temperature. For nozzle wear, especially when printing fiber-reinforced nylon, a hardened steel nozzle is recommended. These solutions are essential for achieving reliable and high-quality prints. Nylon 6 is widely used in engineering applications due to its excellent mechanical properties. It is commonly employed for manufacturing gears, bearings, automotive brackets, industrial fixtures, wear-resistant components, and functional prototypes. These applications benefit from Nylon 6's toughness, flexibility, and thermal stability. Understanding the challenges and solutions in 3D printing, Nylon 6 ensures that these parts meet high-performance standards and are suitable for demanding industrial environments. With proper printing techniques, Nylon 6 continues to be a top choice for advanced engineering projects.